Welcome back to our machine learning project series. In today's video, we are diving into the fascinating world of autoencoders. But wait, we are taking it up by using skip layers to convert a grayscale image to a colorful one. Yes, we are about to add some vibrant hues to our black and white images. Autoencoders are a powerful class of neural networks, commonly used for dimensionality reduction and a data compression tasks. However, they can also be leveraged to tackle the exciting challenge of colorizing images. By combining skip layers, we can enhance the capabilities of our autoencoder and achieve impressive results. But before we dive into the code, let's quickly recap the basics of autoencoders and why they are perfect for this task. An autoencoder is a type of neural network that is trained to reconstruct its input data. It consists of two main parts, an encoder and a decoder. The encoder compresses the input data into a lower representation, often called a bottleneck or latent space. The decoder then attempts to reconstruct the original input data from this compressed representation. But how do skip layers come into play? Skip connections, also known as residual connections, establish direct connection between layers that are non-sequential. By introducing skip layers in our autoencoder architecture, we allow the network to capture and preserve more detailed information at different scales or level of abstraction. In the context of converting a grayscale image to a color image, skip layers help the autoencoder to leverage both low-level details and high-level semantic information from the grayscale input. By incorporating skip connection, the network can combine features from multiple layers, resulting in a more accurate and a visual appealing colorization process. Now that we understand the basics, let's dive into the code and witness the magic of skip layer autoencoder in action. Before we proceed further, let's ensure that we have the necessary environment and resources for our training. In this project, we will be utilizing Google Colab, which provides a convenient platform for running our machine learning code. Please make sure that you have access to a GPU by enabling the GPU runtime in Google Colab. GPU acceleration significantly speeds up the training process, allowing us to train our model more efficiently. You can enable GPU acceleration by going to the runtime menu, selecting change runtime type, and then select GPU as hardware accelerator. Additionally, we will be working with a specific dataset for our grayscale to color image conversion task. You can find the link to download the dataset below. Please note that the dataset is in compressed zip file format. So the first step would be to unzip it before proceeding with the code. You can use the unzip command to unzip the dataset given the directory of your zip file to the directory where you want to unzip the dataset. Now I'm going to run this cell. Now here I have the landscape images dataset, in which I have color images and gray images. Now let's take a look at the module we will be using in our project. Each import brings in a special functionality that we will be utilizing in our code. Let's go through them one by one. Import OS gives us access to functionalities like path handling. Torch provides us with powerful tools for building and training neural networks. Torch Vision offers pre-built dataset, model architecture, and image transformations. Read image helps us to read images from files and convert them into tensors. NN provides a vast variety of pre-built layers and functions for building our own architecture. Dataset, data loader, and random split. These imports give us convenient tools for handling dataset, creating data loaders for efficient data loading, and splitting dataset into training and validation sets. Image folder. This import enables us to easily load dataset organized into specific folder structure. Optim provides us various optimization algorithms like SGD, ADAM, etc. to train our neural network models. Transforms gives us access to a wide range of image transformation that we can apply to our dataset, such as resizing, cropping, and normalization. PyPlot allows us to visualize data. Pill import image provide us with functionalities to handle images. TQDM provides us with the progress bar for tracking the progress of our training loops. Now I am going to run this cell. Before we begin building our autoencoder with skip layers, let's set up a few essential parameters that will guide our training process. Manual seed is equal to 42. By setting a manual seed value, we ensure that we will get the same result, making it easier to debug. We are setting batch size equal to 32. Here we define the batch size, which represent the number of images processed in each iteration during training. Shuffle is equal to true. Setting this parameter to true means that the data loader will shuffle the dataset during the training. Now that we have our parameters set, let's move on to the next step, preparing our dataset. We will create a custom dataset class called landscape dataset to load and process our images. We define a new class called landscape dataset. This allows us to customize the behavior of our dataset. In the constructor method, we initialize the dataset. We specify the root directory where our images are stored. And we list the images present in the color subdirectory. Additionally, we can provide an optional transform argument for image transformations such as resizing or normalization. Length. This method returns the length of the dataset, which is the total number of images in our case. It helps us to determine the size of the dataset and set up our data loader accordingly. Get item. This method is responsible for retrieving a specific image and its corresponding grayscale counterpart at a given index. We load color images and grayscale image path based on the index. The 255 is used for normalization of the dataset. If a transformation is specified, we apply it to both images. Finally, we return the color image and a grayscale image as a tuple. Now that we have our custom dataset class ready, let's move on loading and splitting our dataset. We define a transformation pipeline using transform.compose. In this case, we resize our image to a fixed size of 150 by 150 pixels. Then we apply the specified transformation to our images during loading. After that, we split our dataset into training and test set using the random split function. In this case, 80% for the training and 20% for testing. We created a data loader for the training. This data loader will iterate over the training set in the batches of size. Similarly, we create a data loader for the test set using the same data loader class. This data loader will iterate over the test set in batches. Now it's time to visualize our dataset. We can use this code to visualize our images. As you can see, on the left side, we have our grayscale black and white images, and on the right side, we have our color image. As we can see, we have two types of images in our dataset. The first one is grayscale, the other one is colored. As we progress with our project, it's essential to set up necessary variables and configuration for training our autoencoder with skip layer. We define the number of training epochs, which represent the number of times our model will iterate through the entire dataset during training. Here we set the learning rate, which determines the step size at which our model will perform. Momentum helps accelerate convergence and overcome local optima. If a CUDA available GPU is available, we set the device as CUDA to leverage GPU acceleration. Otherwise, we fall back to using the CPU. Now we will define the autoencoder model that will be used to convert grayscale image to color. Let's take a closer look at the script. This code defines the color autoencoder class, which is a subclass of nn.module from PyTorch. It implements the autoencoder architecture using a combination of convolution and transpose convolution layers. This model has several nn.conv 2D layers for downsampling that represent our encoder, and nn.conv transpose 2D layers for upsampling that represents our decoder. These layers progressively reduce and then increase the spatial dimension of the input image to perform the colorization task. The forward method defines the forward pass of the model. It takes the input X and passes it through the layers of the autoencoder, applying activation function to introduce non-linearity and ensure output values within the desired range. Here we create an instance of the color autoencoder model and move it to the device specified by using .toDevice. This step ensures that computation are performed on the desired hardware such as GPU if available. The second line calculates the total number of parameters. Here we define the loss function using nn.mscloss, which stands for mean squared error. This loss function is commonly used for regression tasks, including image reconstruction. Next, we initialize the optimizer using optim.atom from PyTorch. By setting up the loss function and optimizer, we are ready to train our autoencoder model and optimize its parameter. In this part of code, we define the training group for our autoencoder model. Let's take a closer look at the script. Here, we iterate over the specified number of epochs using the range function. For each epoch, we initialize a running loss variable to keep track of cumulative loss during that epoch. Within each epoch, we loop through the training data using enumerate train loader. For each batch, we move the colored and grayscale image to the specified device. We then make prediction by passing the grayscale image through the model. We reset the gradient to 0 using optimizer.zeroGrad to avoid accumulation from previous iteration. Next, we calculate the loss between the predicted color image and the actual colored images using the defined loss function criterion. The gradients are computed with loss.backward, and the optimizer performs a parameter update with optimizer.step. The loss value is added to the running loss. After each epoch, we print the epoch number and the average running loss. Now we can start our training process. As you can see, our training has started and it will take some time. After the training has done, the result will look like some this. As you can see, the loss is continuously decreasing, which shows that our model is learning. Now we are going to test our trained model and evaluate its performance on the testing data. Let's take a closer look at the code. In this section, we iterate through the testing data using a for loop. We move the color and grayscale image to the specified device, make prediction using the trained model, and calculate the loss between the predicted color images and the actual colored images. The loss value is accumulated in the total loss variable. After iterating through all the testing data, we print the average testing loss by dividing total loss by the number of batches in the testing data. This is our testing loss. Now it's time to visualize the result on the test dataset and see how our model performs in transforming black and white images into the color one. This code can be used to visualize some predictions. As you can see, here is our grayscale image, this is our actual color image, and this is our predicted image. And that wraps our exciting journey through the world of autoencoder and skip layers. For grayscale to color image conversion, we explored the concept of autoencoders and how skip layer can enhance their capabilities, allowing us to bring life to black and white images with a vibrant color. I hope you enjoyed this video and found it insightful. If you did, don't forget to give it a thumbs up and subscribe to our channel for more exciting machine learning projects. We have plenty more objects lined up, covering a wide range of topics and applications.